Hello everyone, I hope you have gone through the previous lecture which was based on stable gravimeters, their working principle and the types of stable gravimeters. In this lecture I'm going to discuss with you about the unstable gravimeters, their working principles and the types of unstable gravimeters. So let's see how unstable gravimeters they work. So unstable gravimeters, they are designed in such a way that small displacement which are generated because of small changes in the value of gravity, it introduces a third force. Third force, this is the third force which is in addition to the two forces that we have, that is the restoring force and the force of gravity. This third force, what it does, it increases the displacement which has been produced by the gravity change. So the third force increases the displacement manifold. So we see the gravimeter here is not restored to its original position, but in fact it is thrown more into instability. So these gravimeters therefore are referred to as labilized, or the more general term, which is the unstable gravimeters. So unlike stable gravimeters, the equilibrium, which is the balancing of the force of gravity with the restoring force, okay, this here is not restored, and the state of inequilibrium between the force of gravity and the restoring force, the force of gravity has increased or decreased, and the restoring force counteracts the force of gravity, but it's not allowed to go into equilibrium, but the state of inequilibrium is maintained by a third force which intensifies the effect which is produced by the gravity change. So here the force introduced because of departure from the equilibrium is proportional to the small changes in the value of gravity if the gravity changes are very small. So the force introduced is also proportional to the small changes in the value of gravity, and this force introduced, it increases the displacement which has been produced by the gravity change. So if the gravity change is in a certain direction, this third force also plays in the same direction so as to reinforce the displacement and thus increase the displacement component. So if we have to summarize in one line, in unstable gravimeters there is a third force which is introduced because of the displacement from the equilibrium position. This third force results in instability of the instrument, which increases the displacement which was produced by the gravity change earlier. So the displacement here is increased because the third force, it reinforces the displacement which was already produced by the small gravity change. So this is the principle behind unstable gravimeters. Okay, we'll first look at the Tyson gravimeter. This is the simplest of the unstable gravimeter. Okay, now the Tyson gravimeter consists of a beam which is attached to a mass at one end and a spring to the other end. There is also an auxiliary mass which is located just above the pivot. Okay, the pivot is represented by the triangle. Now at equilibrium position, that is when the beam is horizontal, the pull of the main spring and the weight of the mass as well as the weight of the auxiliary spring, they are all in balance. So in this condition, that is when the beam is in horizontal condition, there is no turning movement, that is there is no torque or rotation because they are all in equilibrium. But when there is small changes in the value of g, so the mass, that is the weight, changes. The weight which is attached to the beam, it changes. So what happens, the beam slightly gets tilted. So as the beam gets tilted, there is some displacement, very small displacement proportional to the change in the value of gravity in the spring itself. But what happens is the mass just above the pivot, that is the auxiliary mass, it also shifts its position. Now as soon as the displacement is in the spring, and this displacement is also shown by the beam itself, the auxiliary mass shifts, and it then starts to exert a turning movement, a rotating movement in the same direction as the gravity change. Now here the turning movement is represented by the blue line, the blue arrow from the auxiliary mass. So it is acting in the same direction as the change in gravity. So it reinforces the increased gravitational force and produces an additional elongation of the spring. That is, the displacement which was produced by the small gravity change, here it increases because of the turning movement exerted by the auxiliary weight on the beam. Now, displacement of the spring is proportional to the change in the value of gravity, and so there is also deflection of the light source, deflection of the light path from a mirror which is not shown here in this picture, but it's placed just left of the mass m represented by the capital M. So there is deflection in the light beam of that mirror, and this deflection is also proportional to the small changes in the value of gravity. The precision of this gravimeter is 0.25 milligal. So we have seen here the instabilities introduced because of the auxiliary mass. So auxiliary mass in the equilibrium position exerts no turning movement or no torque, but as soon as there is small changes in the value of gravity, there is displacement in the spring, and this displacement shifts the auxiliary mass to a new position where it exerts a turning movement on the beam, and so the displacement in the spring it increases. So this is the principle of Tyson gravimeter, a type of unstable gravimeter. The next type of unstable gravimeter is the LaCoste-Romberg gravimeter. In this gravimeter, there is a weight which is attached to one side of the beam, and the beam is balanced by the mainspring. Now the mainspring here is attached inclined to the beam, and this inclination of the mainspring it introduces the required instability so as to increase the displacement produced by the small changes in the value of gravity. So small changes in the weight because of small changes in the gravity, it moves the beam. So if the weight increases, the movement is clockwise, and counterclockwise when the weight decreases. If the weight increases, the beam is depressed and the spring is further extended. So you can see when the weight increases that the value of gravity increases, the spring also gets extended and the angle between the beam and the spring decreases. But on the other hand, when the value of gravity decreases, the beam rotates anti-clockwise or counterclockwise. The angle represented by 1 between the spring and the beam decreases. It is this angle between the mainspring and the beam which determines the movement exerted by the spring, and the movement exerted by the spring is always in the same direction as the movement which is exerted by the gravity. So if you look at the angle 2, in this case the movement, that is rotating torque or just torque or rotating force on the beam because of the spring, because of the inclined nature of the spring introduced is in the same direction as the change in the value of gravity, that is clockwise. But on the other hand, for the angle 1, what happens is the movement exerted by the spring on the beam is in the anti-clockwise direction. So the displacement produced by the small changes in the value of gravity is increased because of the torque or the turning movement exerted by the spring. Now what is the principle of a zero length spring? So the main spring here is also known as a zero length spring. We know whenever there is departure of the weight from the equilibrium position, there is counteracting restoring force which will try to bring the weight back to its original or reference position. But in unstable gravimeter, we do not need that. In fact, we need it to become more unstable so the displacement increases. Now the restoring force which acts in the opposite direction, it is made small using the zero length spring. So during manufacture, the zero length spring is pre-tensioned so that any restoring force that is there in the spring is only proportional to the physical length and is not equal to any elongation or displacement which is produced in the spring. So that restoring force is already there when the weight is in equilibrium position, that is in the zero position. So in equilibrium position, the weight is balanced, or you can say that the weight is sustained by this opposing tension in the spring. So if there is elongation because of the changes in the value of gravity, that elongation will only be proportional to the change in the gravity and not because of the restoring force that would be acting also. So the restoring force would only be proportional to the physical length of the spring, and not the elongation which would be produced because of the small changes in the value of gravity. So the restoring force here is the pretension that is introduced in the spring during manufacture. Okay. How the instrument is read? The instrument is read by restoring the beam to the equilibrium position by adjusting the screw on the left hand side that can be seen there, which is attached to the main spring, and the vertical location of that adjusting screw is then adjusted so that the beam returns back to its equilibrium position. So what we have seen in LaCoste-Romberg gravimeter is that in the equilibrium position itself, that is when the beam is in horizontal position, the beam is exerting the required tension so as to balance the weight of the mass itself, that is the pretension which was introduced during the manufacturing. So there is already restoring force which is acting within the spring, but that restoring force is only proportional to the physical length and not to the elongation. Elongation only is produced when the weight changes because of small changes in the value of gravity. And so when the weight changes, the angle between the beam and the main spring decreases or increases, and this angle determines whether the turning movement exerted by the spring would be in the clockwise direction or in the anti-clockwise direction. But in this case, what happens when the beam is depressed because of increase in the value of gravity? The angle decreases, and so the movement exerted by the spring is also in the same direction, and so displacement again increases within the spring. In the same way, when the weight decreases because of decrease in the value of gravity, the movement is in the counterclockwise direction, and the displacement in the spring is also in the same direction. So what we see here is the instability which is introduced by the main spring. It increases the displacement which is produced by the small changes in the value of gravity. The next unstable gravimeter is the humble gravimeter. Now in humble gravimeter, there is again a weight which is supported by two springs. One is the main spring and the other one is the unstable spring, that is the auxiliary spring. The main spring is vertical, as you can see, but the auxiliary spring is somewhat inclined, but in the equilibrium condition it exerts its tension through the pivot, and so everything is balanced in the equilibrium condition, and so the adjusting spring, or you can say the unstable spring, auxiliary spring, exerts no turning movement on the beam. So when the beam tilts because of small changes in the value of gravity, what happens is the axis of this spring also gets changes. The axis of the auxiliary spring shifts, and now there is some further tension within the spring, tension or compression depending upon how where the beam has moved. Now this then exerts a turning movement on the beam which reinforces the displacement or the movement which has been produced by the gravity change itself. So in the equilibrium condition, it is the unstable element which exerts its tension through the pivot and so balances the weight or supports the weight in the first equilibrium condition. When the equilibrium changes or the weight changes its position clockwise or anti-clockwise, the unstable element or the unstable spring, the auxiliary spring, shifts its axis, and so when it shifts its axis, the tension now can exert a torque or the turning movement on the beam, and thus it reinforces the changes which has been produced by the small value by the small changes in the value of gravity. The next type of unstable gravimeter is the Mott-Smith gravimeter. In this gravimeter there are two quartz fiber. One is the torsional fiber represented by the blue line. It means it has the ability to twist. The other one is a tensional fiber, that is the fiber represented by the red line which is attached to the weight. So in equilibrium condition, what happens? It is the torsional resistance of the torsion fiber, that is the blue fiber, which balances the weight. And so the tensional fiber which run across the axis of the torsional fiber, that is the blue fiber, the red fiber, which is the tensional fiber that run across the axis of the blue fiber, it exerts no turning movement on the weight. This happens in the case of equilibrium condition. Okay, and so the indicator just below the magnifier is vertical. So if there is change in gravity and the weight falls under that change in gravity, that is increase in gravity, it creates displacement within the torsional fiber, that is the fiber represented by the blue. Since it is torsional fiber, there is twist, there is torsion in the wire. The labelizing fiber which run or pulls through the torsional fiber, then it exerts a turning movement on the weight, and this turning movement acts in the same direction as the gravitational change and is proportional to the magnitude of that change. In the same way, when there is decrease in the value of gravity, the weight decreases, the twist is in the opposite direction, and so the labelizing fiber, that is the tensional fiber, also exerts turning movement which is in the same direction as the displacement of the mass or the direction of the twist, or you can say the direction of the displacement of the mass or the weight. So this was the principle behind Mott-Smith gravimeter. Here the instability is introduced by the tensional fiber, which is the labelizing fiber, also the unstable element. The elements of unstable gravimeters, they are susceptible to temperature changes. Under normal room conditions, the temperature fluctuations are large enough that generates expansion and contraction of the gravimeter elements, and these expansion and contraction of the elements, they are large enough to give rise to spurious gravity readings. So the gravimeters must be operated under constant temperature, and this is achieved using a thermostat system which constitutes an oven that is operated from a storage battery. But the problem with this thermostat system is that it's very bulky and it affects the portability of the gravimeter. There is a complete new class of gravimeters that are referred to as the Warden or the Atlas gravimeter. They are self-compensating and they have no heating oven or anything. But unfortunately, the mechanism of this temperature compensation has not been disclosed by the company which manufactures it. This gravimeter has all of its parts made up of quartz fiber. The hinge beam is already in unstable but equilibrium position, and this unstable equilibrium position is because of the pretension in the zero length spring. So the pretension in the zero length spring has resulted in the unstable equilibrium of the hinge beam. In other words, the pretension in the zero length spring has sustained or maintained the inclination, that is unstable but equilibrium position of the hinge beam. So when there is increase in the gravity, there is gravitational pull on the mass, and it would cause counterclockwise rotation of the beam, when the beam moves in the counterclockwise direction, the hinge beam with the pointer also move in the counterclockwise direction, and the angle between the hinge beam and the pre-tension spring, it decreases. We know the spring would also create or will tend to bring the whole system back to its equilibrium position through the restoring force. This restoring force will be acting in the opposite direction. That is, if the rotation was in the anti-clockwise direction because of the pull of the weight arm, the restoring force in the spring would be in the clockwise direction. So the restoring force, which is in the clockwise direction, which would have been exerted by the zero length spring in order to make the hinge beam reach back to its original unstable equilibrium position, is not achieved because the angle between the pre-tension spring and the weight arm decreases. So the angle between, sorry, not the weight arm, but the pre-tension spring and the hinge beam, it decreases. The decrease in this angle, what it does not allow the clockwise movement of the pre-tension spring, that is the restoring force, to act on the beam in order to restore back its original position. That is, it maintains the instability that is produced by the small change in the value of gravity. So the weight arm, when moves downward, the hinge beam also move in the anti-clockwise direction. That is, weight arm move in the counterclockwise direction, the hinge beam also moves in the counterclockwise direction. But the restoring force in the pre-tension spring would be exerting a turning movement on the hinge beam in the opposite direction, in the clockwise direction. But since the angle between the pre-tension spring and the hinge beam, is lessened, this turning movement, or the clockwise turning movement, cannot be exerted on the beam because the angle is reduced. Keep that in mind, that the turning movement depends upon the angle. It's very dependent upon the angle. As soon as the angle it decreases, between those two elements from which the torque or the turning movement exerts from one place to the other, one point to another. For example, here the torque or the turning movement will be produced by the pre-tension spring on the hinge beam. But since the angle between the two has reduced, the torque depends upon the angle. When the angle gets reduced, the turning moment also reduces, and so the equilibrium is thus not maintained. Here the equilibrium is already unstable because the pre-tension spring has sustained the unstable equilibrium or the inclination of the hinge beam. So when the angle decreases, the clockwise turning movement of the pre-tension spring, which would have tended to maintain the equilibrium position of the weight arm, cannot be achieved, and so it throws the whole system into instability. And this type of gravimeter can read up to 0.01 milligauss. At last, one thing we finally need to know is the calibration of gravimeters. The gravimeters, like any other instrument, they need calibration because the scales of the divisions, the scales or the divisions of the scale on the gravimeters, they are arbitrary. We don't know what we are measuring when we measure through gravimeters unless it is calibrated. So there are divisions, but we don't know what is the values of gravity that the gravimeter is measuring. So the best method to calibrate gravimeter is to take readings at 2 points where we already know the absolute or relative changes in the value of gravity through pendulum observation. So the differences in the pendulum observation between the absolute value of gravity, if this is a fraction of the total range of the instrument, that is, for example, if the differences between the two absolute measurement of the gravity is 2 and the total range of the gravimeter is 10, okay, so the difference in the gravity value is 2 and the total range of the gravimeter is 10. So 2 is a fraction of 10. So the scales or the divisions of the scale on the gravimeter, that is 10, can be divided into 2 each. That means we will have 5 divisions of 2, let's say milligal each. So in simple words, it's the gravity value difference at 2 locations that are used to calibrate the scale divisions of the gravimeter. So this was all about your unstable gravimeter, the principle and the types of unstable gravimeter. I would encourage you to go through this lecture at least 2 or 3 times so that you are able to grasp the concept fully. I would also encourage you to go through the book, which is the book by Dobrin, Introduction to Geophysical Prospecting. And in the previous lecture, which was on the stable gravimeter, these two topics along with the torsion fiber and the pendulum makes your 3.1, and these are the instruments that we use in gravity prospecting. The most important instrument are the gravimeters that we have just covered in the last 2 lectures. Please go through it, and if you have any question, you can message me or you can mail me. My email ID is sumit.lay@gmail.com. Please go through these lectures, and I hope I will see you in the next lecture. Have a nice day. Thank you.